Hello, Chem 1B. This is Chapter 18, Lecture Video 5, and we're going to be covering Gibbs free energy. So, if you have taken some biology courses, you might have heard of this term Gibbs free energy or free energy. It's a very important component in a lot of in understanding biological systems. Now, this equation here is our delta S of the universe equation. Now, I've rearranged it a little bit. I've basically plugged in for delta S of surroundings, right? Because we know that's equal to negative delta H of our reaction or system divided by T. And so I've plugged that in here. Now, one of the interesting problems with this whole thing is that this component here is in joules per mole per Kelvin, and this is in joules per mole per Kelvin, and then this is in joules per mole per Kelvin, and that per temperature unit in the denominator is really troublesome. Generally, we'd rather it be in joules per mole or just joules when we're looking at these types of systems, because we want to know how much energy is either being formed or required or whatever for our system. So we're going to rearrange this equation by multiplying both sides by negative t. Now, if I do that, if I multiply both sides, I get a new equation, and it looks like this. All right, the t cancels here, and it comes in here, and this whole thing turns into this equation. Now, in this equation, everything is in just units of energy, right? Because delta S is joules per mole per Kelvin, and temperature's in Kelvin. Notice when these two are multiplied together, the Kelvins cancel. Delta H is always just in joules per mole. And the same thing is true here. Now we're in joules per mole here. So this is a much more favorable situation because everything's in energy units as opposed to energy units per temperature. Now, so what does negative T delta S universe actually mean? It's defined as the free energy available after the reaction kind of takes into account entropy, right? You can kind of think of it as the energy that's left over and available to do work. Now, generally, instead of saying negative T delta S universe, we just call this delta G, or the Gibbs free energy for our system. Cool, so let's move on. So the Gibbs free energy equation, just like delta S naught of the universe, combines two driving forces of spontaneity into one term, entropy and enthalpy. Now, lowering Gibbs free energy, in other words, having a smaller delta G naught, is a driving force for chemical change, often called chemical potential. So how much potential you have for a chemical reaction to occur. Because of this, when delta G naught is negative, a process is spontaneous. And this is now the third way we know to determine spontaneity. So we can do delta S universe, that's positive for spontaneous processes. We have now delta G naught of our reaction is going to be negative, and our equilibrium constant is going to be greater than 1. If our process is spontaneous, all three of these things will be true. Not just one of them, all three of them. So for instance, if I have a positive delta S universe, this means I will have a negative delta G naught. And it means I will have a K value that's greater than 1. Let's get this out of the way so we can actually read. If delta G is positive, obviously that means the process is going to be non-spontaneous. So let's talk about this a little bit more, right? The Gibbs free energy change for a reaction varies with temperature because of this T here. However, we can use tabulated values of delta G naught of formation at 25 degrees Celsius. If we want to calculate a delta G naught at 25, we can do the same thing we've done with the other values, delta H and delta S, and do, hey, the sum of our delta G naughts of formation of the products times N minus, epsilon value delta G naughts formation of the reactants times N. This equation works with delta G naught as well, but it only works at 25 degrees Celsius because that's what the delta G naughts are tabulated at. And so that's kind of an important thing to understand, because you can only use this equation for delta G under certain circumstances. And those circumstances are, you got to be at 25 degrees Celsius. Just like with delta H naught of your formation, delta G naught of formation is defined as free energy change to form 1 mole of a substance from elements in their standard states. Now, if you don't remember delta H naught of formation, just cross out free energy here and put enthalpy. And then boom, you have the same definition, just one word different, or 2 words different. Delta G naughts for elements in their standard state is still 0. It's a null reaction. This is defined. This is just like delta H naught of formation as well. Cool. So in other words, if we were looking at like O2, oxygen gas's delta G naught of formation would be equal to a 0 value. So if you're ever thinking like, hey, Professor Cullen didn't give me delta H naught of formation of this thing and I need it in the reaction, or I didn't give you one for delta G naught of formation and you think you need it, ask yourself if that is an element in its standard state, because then that's why I didn't give you the value. You should know it will be 0. All right, what if, so that's great. We can use delta, like products minus reactants, to get delta G naught of reaction at 25 degrees Celsius or 298. But what if I'm not at 298 Kelvin? What can I do? Well, that brings us back to this equation here. I can solve for delta H and delta S at 298 using the values that are tabulated. And we can actually just plug those straight into this equation, even though they're not calculated at the correct temperature. It's a pretty good assumption to make. Both delta H and delta S, they do vary with temperature, but very, very little. It's a very small variation. And in addition, a lot of the variations between delta H and delta S tend to cancel each other out a little bit. So we typically will just calculate these at 298 and plug in whatever the heck temperature we want here to solve for delta G at that temperature. In other words, we're going to solve for delta H at 298, delta S at 298, then plug whatever temperature we want. 600 Kelvin, sure, put that there. And then this would be 600 Kelvin's delta G. This assumption is going to give you okay results for the most part, and at least for our purposes it will give you okay results, because we don't actually learn how to determine delta H at a different temperature or delta S at a different temperature in this class, other than by measuring it in the classroom itself. So basically the whole process would be we'd solve for this, plug in the temperature, solve for delta G. Okay, so let's do a problem where we calculate delta G of reaction, right? So in this case, this is actually saying, hey, we're at 400 Kelvin here, so we know that. And we want to know what delta G naught for this reaction is at 400 Kelvin for this reaction. The first thing to do, as we know, delta G naught of our reaction is equal to delta H naught of our reaction or system minus T delta S naught of our reaction. All right, so if I want to solve for this, I have temperature already. This is going to be 400 K. What I really need is delta H and delta S for my reaction, and I can get that using Hess's law, right? So I need to look up here all the delta H naughts of formation. Now for oxygen, we know it's going to be equal to 0 because that's a definitional thing. And I also need to look up all the S naught values here for this so that I can plug into products minus reactants, solve, and I'm going to get these two values if you do that out using tabulated stuff. Now on a test, I would be giving you those values in like a table, and you just have to apply the formula to solve for them. Now, one of the things we do here is we always, regardless that these are actually at 298, we assume that delta H and delta S do not change very much over temperature range. So we're just going to use them as though they are at 400 Kelvin. And that's what we're pretty much always going to do. Now, the other thing to make sure to take into account here, and it's a very common mistake, is this kilojoules joules thing. We need to convert one of them to the other's units. It really doesn't matter which one we go about doing. In this problem, you kind of see here, I'm dividing by 1,000 in the expression, and this is to change joules to kilojoules. At this point, we just kind of plug into our equation. The delta H goes here, the delta S goes here, 400 Kelvin goes there, and I'm dividing this by 1,000 to get it into kilojoules. This gives me a delta G naught of my reaction of negative 974.7 kilojoules per mole. This tells me this reaction is this reaction is spontaneous, because as we know, delta G naught when negative is a spontaneous system. So this is a spontaneous reaction here, which is kind of neat. All right, so if you guys have any questions, as always, email, or even better, our Zoom discussion sessions.